All right, I'm going to be going over this problem. A disease test is advertised as being 99% accurate. If a person has the disease, they will test positive 99% of the time. If you don't have the disease, you'll test negative 99% of the time. 1% of all people have the disease. Now a patient tests positive. What is the probability they actually have the disease? So I'm going to be using what's called a 2x2 table, which I really like. So conditional probabilities can be broken down in these 2x2 tables. And across the rows and columns, you put the two conditions. So the two conditions, the first condition is whether you have the disease. So you can either have the disease or you can not have the disease. And these probabilities should add up to 1. So you either have the disease or you don't have the disease. But it's going to be one or the other. And then whether you test positive or not. This is the other condition. So you either test positive or you do not test positive. So let's go through these different bullets. If a patient has the disease, they will test positive 99% of the time. So this means probability that given a patient has the disease, so given they have the disease, so D positive, they will test positive 0.99. So given they have the disease, they will test positive 99% of the time. And if you don't have the disease, so this is given the negative, they will test negative 99% of the time. So test negative 99% of the time. And then 1% of all people have the disease. So this would be, if you have the disease, this would be 0.01. And these have to add up to 1. So 1 minus 0.01 equals 0.99. So given the probability, 1% of all people have the disease, so 99% of people do not have the disease. Cool. So there's another way of writing Bayes' theorem that I want to show. Theorem. So you commonly see this, but here's, I don't really like the way they have that formatted. Yeah, this is it. So probability of x given y, and that's not any bigger, but it's probability of x given y is the probability of x and y over the probability of y, and that's the formula that I'm going to be using. Excuse me. So probability of test positive given D positive equals, by this formula, probability of test positive, and I'm going to use an and. Excuse me. And D positive over D positive. So if we fill in what we know this part right here is 0.99. And we don't know this part, but this part on this 2x2 table is this box right here, test positive and D positive. Test positive and D positive. Apologize. Really struggling to write with this. And probability of D positive is 0.01. So we can multiply this by this to get this. 0.01 times 0.99 equals 0.0099. And this column right here needs to add up to be 0.01. So if I do 0.01 minus this, I will get this box right here. 0.01 minus what I just did. And this is 0.0001. And let's do the same thing for this equation right here. Probability of test negative given the negative equals probability test negative and D negative over probability of D negative. So fill in what we know. This part right here is 0.99. This part right here is an unknown, but this is test negative and D negative. So this is this box right here that we'll fill in. Test negative and D negative. Probability test negative and D negative over the probability of D negative, which is 0.99. So multiplying across, 0.99 times 0.99, 0.9801. And excuse me. So I can add across. Let's actually just fill in this box right here. So this box plus this box has to equal 0.99. So 0.99 minus 0.9801 will give me this box. Minus 0.9801. This is 0.0099. And then adding across these rows, I got 0.099 plus 0.0099. So I get 0.0198. And adding across 0.001 plus 0.9801. There's 3 zeros. 0.001 plus 0.9801 equals 0.9802. And as a sanity check, these two values have to add up to 1. 0.9802 plus 0.0198, it looks like they do. Perfect. So this is the probability that someone tests positive is 0.0198. The probability that someone tests negative is 0.9802. The probability that someone, excuse me, that someone has the disease and tests positive is 0.0099, so not very high. Then the probability that someone has the disease and tests negative is 0.0001, so really small, but much larger, much smaller than this value. Probability that someone tests negative and does not have the disease, 0.9801. Probability that someone tests that does not have the disease and tests positive is 0.0099. So something to keep in mind here. This value is exactly the same as this value. So if you, whether you don't have the disease or do have the disease, your probability is exactly the same, which is kind of interesting. So let's solve this problem now. So we want probability that you actually have the disease. So you test positive, so probability that given you've tested positive, you actually have the disease. So that would be D positive. Cool. So I want probability of D positive and T positive. So, and then I want the probability of T positive. So let's fill in what we know. D positive and T positive is this right here, 0.0099. That's 2 nines over the probability of T positive, 0.0198. And this equals, I believe it's 0.5, and it looks like it will. 0.0099 divided by 0.0198 and 0.5. So we can kind of see it here that given that you've tested positive, you have an equal chance of having the disease and not having the disease. So this is using a 2x2 table. So hopefully this was helpful.